The SamplLab at the Weizmann Institute of Science focuses on developing new technologies for efficient signal acquisition and processing across various applications, including medical imaging, radar, and communication. Our current focus is on introducing green analog to digital converters. Real-world signals are typically analog but analyzed digitally in modern signal processing systems. Consequently, analog to digital converters, ADCs, are crucial in this process and widely used in various applications, such as sound transformation in hearing aids, conversion of light data from cameras, representation of heartbeats in implantable cardioverter defibrillators, ICDs, and translation of radar data from systems with multiple antennas. Traditional ADCs face several challenges. The first challenge involves high sampling and quantization rates, leading to significant power consumption, expensive hardware, and increased data processing needs. The second challenge is accommodating the signal's dynamic range within a fixed bit budget and noise settings. Setting the dynamic range too high risks drowning out weak signals, requiring numerous bits and complex hardware, as seen in hearing aids, missing low-amplitude voices and noise. Conversely, setting it too low can clip strong signal components, such as high-intensity light captured by cameras, leads to images with low dynamic range. Another challenge is the requirement for a high-speed global clock, which increases power consumption, number of bits, expensive hardware, and susceptibility to electromagnetic interference. For example, in an ICD's ADC, a high-speed clock accelerates battery depletion, necessitating surgical intervention within a decade. We present 4 new energy-efficient sensing approaches resulting in green ADCs. Sub-Nyquist sampling to reduce sampling rate. Task-based sampling to reduce the number of bits based on the task. Modulo sampling to allow unlimited dynamic range with a small number of bits. Time encoding machine to sample without a clock. Sub-Nyquist sampling. The fundamental sampling theorem dictates sampling at twice the signal's bandwidth for perfect recovery. However, traditional methods may lack efficiency, as seen in radar and ultrasound systems, which offer inherent signal structures. The advent of sub-Nyquist theory introduces a revolutionary approach leveraging the unique signal structure, allowing for simpler ADCs with significantly reduced sampling rates below Nyquist. For example, we demonstrate a sampling-based hardware prototype enabling radar signal sampling at rates 30 times lower than Nyquist. Our prototype ensures reconstructed target scenes maintain high resolution despite low sampling rates even in noisy environments. Additionally, we develop a hardware prototype for single-input, multiple-output sub-Nyquist radar, estimating target range and amplitude from samples measured at 10 times lower than the Nyquist rate, without requiring knowledge of the pulse shape. Furthermore, we present a sampling-based hardware prototype designed to produce high-quality and clinically viable ultrasound images at significantly lower sampling rates using an efficient portable device. This innovation enables ultrasound machines to operate wirelessly using only a compact portable probe. These innovations extend to cognitive sub-Nyquist MIMO radar and MWC cognitive radio prototypes. In summary, sub-Nyquist sampling facilitates the construction of practical ADCs with substantially reduced rates below Nyquist. Task-based sampling, TBS. In signal sampling applications, our focus often lies on task-based analyses, which involve specific functions derived from the signal itself. For example, in wireless communications, we prioritize reconstructing transmitted signals over raw received signals at base stations. We employ this task information and introduce an analog combiner for pre-processing received signals to reduce sampling and quantization rates. We propose a hardware prototype for 2-user signal recovery using a 16x2 analog combiner to pre-process signals before ADC. This approach reduces memory by 25-fold, requiring only 2 low-resolution quantizers instead of 16, without compromising signal recovery performance. To conclude, task-based sampling leverages task-specific information to minimize the required number of bits. Modulo sampling. We present the Modulo ADC, designed to effectively handle high dynamic range signals while operating close to Nyquist rate with reduced number of bits. In this system, we pre-process the high dynamic range input signal using a non-linear modulo operator to fit within the ADC's range. Then, post-ADC processing involves a recovery algorithm to extract true samples, completing the signal reconstruction. We provide different recovery algorithms with the aim of improving the performance in terms of computational efficiency and robustness while operating close to the Nyquist rate. We implement these algorithms using a dedicated hardware prototype. Further, we showed that our board and methods enable sampling high dynamic range signals with simple low-rate ADCs and a small number of bits. Time encoding machine (TEM). Time encoding ADC eliminates the need for a global clock by encoding time intervals in which the signal's integral passes a predetermined threshold, significantly reducing the power consumption and electromagnetic interference. We introduced the first asynchronous integrate and fire time-based hardware implementation, equipped with an efficient recovery algorithm and with the ability to operate at sub-Nyquist rates. Our focus extends to structured signals like ECG and show that sampling rates can be set below the Nyquist rate, similar to synchronous sampling advancements. Our TEM implementation simplifies ADC design by eliminating the global clock, reducing power consumption and required bits while ensuring accurate signal recovery. In summary, sub-Nyquist sampling efficiently captures data at rates lower than traditionally required by leveraging signal structure. Task-based sampling reduces power consumption of high-resolution quantizers by reducing the number of required ADCs and the number of bits in each ADC by exploiting the ultimate signal task. Modulo ADC efficiently manages signals with a high dynamic range, accommodating both weak and strong signal components within a fixed number of bits. Time encoding ADC eliminates the need for a global clock, enhancing power efficiency and reducing required bits. To learn more, visit the SamplLab website.